So our next unit deals with objects called vectors. They are something that are used very frequently in physics, for example. So for those of you that have taken any physics, you've been introduced to the concept of vectors. But vectors are basically just directed line segments, as it says here in our first statement there. What we mean by that is it's a line segment that represents two things at the same time. It's going to represent the magnitude, so that's going to be communicated by the size of the vector, the length of the vector, and it's also got a direction associated with it. It's not just a line segment, but it's a directed line segment, and so that's going to be represented by an angle, which is going to be measured the same way that we have in our trigonometry study, from the positive x-axis rotating counterclockwise. So again, the key piece though is this idea that it has both of these elements, a magnitude, a size, and a direction. And that differentiates a vector from something called a scalar quantity. And so a scalar quantity is something that has a magnitude, but it does not have a direction. So one example of that would be volume. Right? So the volume of a box does not matter what the orientation or the direction of the box is. So that is something that has volume or magnitude but not direction. Time would be another example of a scalar. Although time moves forward, it does not really have a direction associated with it. On the other hand, the velocity of a truck that's driving down the road, that's something that has magnitude, whatever speed the vehicle is traveling at, and there's a direction oriented associated with it. Wind is another example, so the speed of the wind and the direction in which it is blowing. Or a vector could represent just the pathway that someone is moving. So the distance that they travel would be the magnitude, and then of course the direction that they travel. So that's kind of the difference between vector and scalar quantities. So down below we can see a couple pictures of vectors. The arrow at the tip of the vector represents the head of the vector or the tip of the vector, and then wherever the vectors kind of initiates from, like where it starts from, is called the tail or the beginning point of the vector. So we can see that in both of those diagrams below. Pretty much as many textbooks as there are for math and physics, there are that many different notations used to represent vectors. So for our purposes, we're going to see kind of a couple things in the textbook. They tend to use bold letter to represent a vector. That's kind of hard to do when you're just writing. So typically I'll use a variable, lowercase variable, with an arrowhead above it so that we know that we're referring to a vector. If we're just talking about the magnitude of a vector, so what is the length of the vector, what is the speed that it is representing, or the distance that's being traveled that it's representing, again, there's several ways that we'll see that depending on the textbook we're working with. But it's referred to as its absolute value, so sometimes you'll see just a single absolute value bar around it. Our textbook leans to using a double bar surrounding the variable representing the vector. And then two vectors are considered equivalent to each other. They're considered equal if they have the same magnitude and the same direction. But they don't have to be starting from the same initial point and ending up at the same ending point. So for example, for the diagram that we see in the first one, if I had a parallel vector drawn right there that had the same magnitude, same length, and was oriented in the same direction, those would be considered equivalent vectors, even though they're starting and ending in different places. And then finally, we say that a vector is considered to be in standard position if its beginning is at the origin. Another term for that is it'll be called a position vector. So a position vector is one that is starting at the origin and indicating a distance to some other point. Otherwise, if it's just from one point to another, that would be a displacement vector. So we can see in the first example that would be one that is a position vector because the initial point is at the origin, whereas in the second example, that would be considered a displacement vector because we're just traveling from some other point in the coordinate plane to that finishing point. But again, the key information about a vector is that it represents a direction and a magnitude. So in the case of the first example that we see here, for us to figure out the properties of this vector, we need to know what the length of the vector is. So we can see that we're traveling 8 units in the horizontal direction and 4 units in the vertical direction. Dropping that perpendicular there, we can see that we have a right triangle. So we can just use the Pythagorean Theorem, little 8 squared plus 4 squared, and then take the square root of that result to figure out what the magnitude of the vector here is. And so if we do that calculation, we get 8.9. And so that could be in either meters, if it's just a distance that we're showing, or inches. It could be a speed, 8.9 miles per hour, or feet per second, just depending on the context of the particular problem. And then for the direction, as is our usual from the previous unit, we're going to measure the direction of the vector from the positive x-axis rotating counterclockwise. So for us to figure this out, we've got a horizontal side of 8, we have a vertical side here of 4, and so we can just do a little inverse tangent of 4/8 to figure out what the measure of that angle is. And so if we do that on our calculator, we'll see that we get 26.6 degrees. Sorry about that. Fix that there. So it's pretty easy for us to find those values, the magnitude and the direction, for a vector that is in standard position. What's a little bit trickier is if we have a displacement vector like we have on the next one. It's not really going to be any different in terms of how we approach the calculations, but we do need to kind of recognize that it's measuring our angle is going to be a little bit trickier, especially since it's not pointing up into the first quadrant. So one thing that we can do here is we can kind of imagine that we have like a coordinate plane right here, like translate things so that the origin is there at the initial point of our vector instead of where it is kind of off to the left. And so from here then we can build our right triangle like we had on the previous one in order for us to be able to figure out what the magnitude is. So we just need to subtract the x coordinates and subtract the y coordinates to figure out what the horizontal and vertical sides of this triangle are. So for the x direction, we've got a length of 2 that's right there. And then in the y direction, that vertical side is going to be 8. And even though I'm traveling to the left and down, it doesn't really matter that I indicate those right now as being positive or negative, because I'm really just using them for the Pythagorean Theorem. A little 2 squared plus 8 squared, so take the square root of that, and we're going to get a magnitude of this vector equal to 8.2. And then for the direction, it's got a little bit of a two-step process to get there. So it's not just that angle that we're interested in. We need to get all the way around from here. But we can start by finding that small reference angle and then adding 180 to it. And so if we do a little inverse tangent of our reference angle, we're going to find that that is 76.0 degrees, if we round off to the nearest tenth correctly. And so then again, that's not the direction of the angle. We need to make sure that we're measuring it from the positive x-axis and rotating around. Otherwise, there would be no way for us to know that this vector is pointing down and to the left instead of up and to the right. So if we add 180 to that, now we get the true direction of this vector, which is 256 degrees. So magnitude and direction are those two key elements for a vector. You can't just have one or the other. You need to have both.